Hello and welcome to the tutorial Simulation of Large-Scale Computational Ecosystems with Alchemist. This tutorial is organized in 3 sessions. It will be more or less 20 minutes each, at the end of which there will be a Q&A session of about 10 minutes. My idea is the following. I would like to first tell you which are the requirements for performing the tutorial along with me. It is meant to be interactive, as interactive as possible, considering the situation in which we are having this tutorial. So the idea is that you should be able to follow me while I present examples to you, and maybe we can interact a little bit in the Q&A session after my presentation. So before explaining to you what this simulator does, what does it simulate, I'd like you to be ready with the tools for the moment in which we will have the examples to discuss. You don't need much. There are 2 tools that I recommend. One is actually optional. The optional one is Git. Git is a distributed version control system. You likely have it already installed. At least if you use Linux, it's probably pre-installed. To test if it works, I guess git ---- version. If it prints something reasonable, you then probably already have Git installed. It's my case. If you don't, if you're on Ubuntu, I guess it's something like apt-get install git should work. For other systems, my suggestion is to go to git-scm.com, and from this page you should be able to download it for multiple systems. It supports Windows and Mac as well, so you just download it and install it, and you can do it while I am explaining how the simulator simulates. The second part that you need, and this is not optional, we can work around Git, we cannot work around that. You need Java at version 11 or above. So in my case, Java ---- version, it's version 11 right now. I could actually use a newer one, but anyway, Java 11 is just fine. If you do not have Java installed, you need it. My suggestion is to go to adopt OpenJDK, and from there you can download it. You can download the latest version or the LTS version. Just don't use Java 8 because Java 8 is outdated. The simulator doesn't work with Java 8, so make sure, even if you print Java ---- version in your terminal and it tells you that the version is before 11, the simulator won't work. So update Java. You can download it from there. If you use Linux or maybe also macOS, there are alternatives such as Jabba, like Jabba the Hutt. It's an installer for Java. It installs Java in user space. If you search for Java GitHub, it's this one. I'm pasting the link here so that it's easier to read. I'm using the terminal as a text editor. So you can visit this website, follow the instruction to install a recent version of JDK. Anyway, I expect most of you to have a decently recent version of Java. Java 11, as said, is fine. So let's talk a little bit about the simulator. We conceived the simulator for a European project, Sapere, in which the idea was to coordinate multiple devices. Those devices were situated in the environment. They were equipped with sensors and actuators, and the idea was to program them with a metaphor resembling ecosystems, namely writing so-called eco-laws that must have governed the progression of the simulator. Usually systems like this one get simulated by using agent-based simulators. One very famous one is Past. Many experiments that I've seen in my career were done in NetLogo. There are others as well, Argos. Our problem with those simulators at the beginning was mainly performance. And the reason was that we wanted to scale up to tens of thousands of nodes, and that was quite difficult to do. So the idea was to, rather than have a very, very expressive simulator like Repast, in which you basically program whichever behavior you like, to take the opposite approach. Usually you take an agent-based simulator which is expressive enough to allow you to write your simulations, and after you created them, you try to optimize. We try to do the opposite. So starting from simulators which are known to be very fast, try to extend them to the point that we could simulate our system. It's a bit of a different approach with respect to other simulators in the literature, but fortunately it was successful. We began creating the simulator 10 years ago, more or less. It was my master thesis, and then it grew a lot actually in these years, and it was used in many works in the literature, more than 50 for sure. So we began from the simulators for biochemistry, and in particular actually for chemistry. There's the famous Gibson-Brook, if I don't mistype it, Gibson-Brook algorithm from this paper, which introduces a method to optimize the well-known Gillespie procedure for simulating basically Markov chains that evolve with chemical Reich rules. Our system was similar at the beginning, so we tried to say, okay, let's start from that algorithm and let's expand it to support a richer system. Which kind of system did we need? Basically we needed a bidimensional space. If you can read the image here, I actually wrote Riemannian manifold. It's a very fancy word to say it's a Euclidean space but supporting holes, or Euclidean space in which distances can be a little bit strange, like the distance from A to B can be different than the distance from B to A. That's actually not so strange. Imagine just a street map. So you might have a distance from A to B with a single sense road in a direction. So if you get from A to B, maybe it's a straight line, but from B to A you need to take a longer tour. And as you see, the overall manifold doesn't behave exactly as a Euclidean space. That's the reason why the environment in Alchemist is a little bit more generic. The environment contains nodes. Nodes are linked together by a linking rule that basically associates the state of the environment and its node with the set of other nodes that are considered to be its neighbors. Currently, neighborhoods in Alchemist are bidirectional, so if some node A is a neighbor of B, then also B is a neighbor of A. This is something that we plan to relax in the future, but for now the relationship of neighborhood is symmetric. Nodes contain molecules. You can think of molecules as just names, tokens. Molecules are connected to concentrations. Concentrations are the actual data item contained inside the node. You can think of concentrations and molecules as variable names, molecules, and actual data associated to the name concentration. Crucially, all nodes also host reactions. Reactions are the only events that make the simulation progress. How are they made? Obviously, we inherit a little bit of the nomenclature from the original Gibson-Brook work, from which we inspired the Alchemist engine. And that work was focused on exact stochastic simulation of chemistry. So, of course, we use the term reaction to identify the events that can evolve the state of the system. An Alchemist reaction is composed of a set of conditions, which are basically predicates on the environment, that cause a set of action, a set of changes in the environment. Conditions can be whatever. You can ask if the node in which I'm hosted currently has some particular concentration associated to a molecule. You can say, okay, this reaction is enabled if I have at least 10 neighbors, or any other arbitrary condition on the environment. On the action side, any change in the environment can be expressed, so it could be a change in the concentration, it could be a movement of the node inside the environment, so a change in its position, it could be any other arbitrary modification of the environment. Reactions do not trigger as soon as the conditions are met, but rather they are scheduled according to a time distribution and a rate equation. The time distribution, is a time distribution. It's a distribution of times. It determines how often the reaction would happen if the conditions were constantly met. The rate equation allows conditions to return values and to influence this time distribution. So you might say something like this particular reaction triggers quicker if the node is moving at above a certain speed threshold, or this reaction goes quicker as the node moves quicker. Of course, the original engine was not supporting this kind of model, which is way richer. In the original work, it's plain chemistry, so there's a single container of molecules, concentrations are plain integers, and the whole algorithm is optimized in order to speed up the execution of these reactions. In Alchemist, the model is more complex, so we had to make a number of important tweaks to the original algorithm that, of course, make it slower, but also allows us to retain much of the original speed and support the world we want to actually simulate. So the first difference is that both conditions and actions express contexts, which mean for conditions where they do read values, for actions where they can make changes. This is useful for us for restricting the number of events whose scheduling may change in face of an event. Imagine, for instance, the case of a reaction that whose speed gets higher with the movement of the node. And imagine this reaction is programmed onto a smartphone, which is weared by a person walking. If at some point the person walks faster, which in Alchemist would mean that there is some reaction modeling the movement of the person that gets triggered more frequently or makes larger movements at every shot. As a consequence, the first reaction should accelerate. This is intercepted through a network of dependencies, and the simulator needs to know what some reaction reads or writes in order for it to build a dependency graph and speed up the execution of the simulation. One key element of Alchemist is its extensible architecture. Rather than forcing the user to express the behavior of the reaction in some predefined language, we decide to abstract away the definition of concentration. Basically, the whole simulation infrastructure is generic with respect to the type of concentration. And defining the type of concentration and the default way of writing reactions is up to the so-called incarnations. There are currently 4 maintained incarnations in Alchemist. The first one is Biochemistry, in which concentrations are floating point numbers. We used it for experiments related to biology. It's actually simple from the point of view of the concentration, but it includes rather complex elements that mimic the workings of biological systems. I'm not very expert on that, but I had colleagues that were expert in biochemistry and guided us to do a correct implementation. So, for instance, this is a simulation of a morphogenesis process in which gray cells, which are initially undifferentiated, get their specific type, and if we let the simulation run, they should basically create 4 types of tissues. This is programmed basically as a genetic network. I'm not very expert on the topic, so I won't deep dive into it. But the simulator is able to support this kind of behaviors. The second incarnation was made for the Sapere European project, and we will use that in the tutorial beginning from the second part of this presentation. In the Sapere incarnation, concentrations are set of tuples matching some template. In the original project, the idea was to rely on a pattern matching lambda-like way of manipulating data items. And so we made the simulator in such a way that molecules were tuple templates and concentrations were the set of ground tuples matching such a template. This allowed us to build a simple language for writing, basically rewriting rules based on the content of nodes. We will be experimenting with that in some time. More recently, there are 2 additional incarnations that we made in order to support aggregate programming. Basically, there are 2 languages for aggregate programming. One is Proteus, which was the say older of the 2. I guess it's proteus.org. Yeah, proteus.org. Yup, that's one of the 2 languages, and the other one is Scaffi. They are actually similar. Scaffi is an internal DSL for Scala. Scaffi aggregate DSL. Let's see if there it is. Scaffi, as said, is a Scaffi internal DSL. We won't be experimenting with Scaffi directly, but it's not hard to do. It's something which is supported as well as Proteus. We'll be using Proteus mostly because I'm a little bit more used to it. But they can be both used inside the simulator easily. Aggregate programming languages are meant to let the designer specify the behavior of the whole network of devices coherently from a top-down global perspective. The languages figures out how single devices should coordinate to carry out the result that's desired. We conceived those languages after the simulation had been realized, but fortunately we noted that the architecture was extensible enough to support the simulation of this kind of systems. So we were pretty happy with the overall result. I'll let you see some experiments that we done in the past. So, for instance, let's see. In this case, we are navigating these nodes along the streets of London. There's an area which is marked as undesirable, which is this red area here, and nodes just do a gradient descent and reach the final target, which should be in this area. This is a little bit, that experiment was written with the Sapere incarnation. This experiment instead is based on real-world GPS traces from the Vienna City Marathon in 2012, I guess. In this case, nodes are computing a crowd warning program. Nodes which are depicted in the reddish shade are in a risky zone. As you can see, at some point we inject a different version of the program, which is depicted in green. The original version of the program is in blue. We inject it from a node, and we program it to propagate along the network. So some nodes from blue turn green, and as you can see, the red shade becomes less present. The reason is that we basically just change the parameters for defining something as overcrowded or not. This is an example of hot code injection, which is something Aggregate programming supports, and of course Alchemist is able to simulate. Crucially, if you write something in Protelis or in Scaffi, unless you use some, you can always screw up things, but if you use the languages as you're supposed to, the code that you test in the simulator is exactly the same code that you will deploy once you find that the simulations work as you expect. I'd say that we can call it for the first part of the tutorial. It's the only theoretical part. We will begin getting our hands dirty in the second and third part of the tutorial.